this section deals with simplification of a force and couple system. So there are two objectives for this section. The first objective is to know how a single force acting on a body can be simplified to a single force and a couple moment. So for example, let's say you have an X, Y, Z coordinate system, and there's some kind of body where a force F1 acts. Let's say there's another force F2 and perhaps even another force F3. And what we want to do is now say, can we reduce this system such that it can be represented by a single force and a couple moment? Meaning, here's that same body again. So can these forces be represented as a single force and a single couple moment? Meaning, can we somehow reduce those three forces to a single resultant moment and a couple moment, MR, that acts at point O? So what we want to do is know how to do this and what is the meaning of this. So let's take a look at the how first. So suppose you have some kind of, let's say a stick, and a person is holding it, and there's a force that's applied at the end of the stick. So we know that this force causes the stick to have a tendency to rotate about, let's call this point A. So force F causes the stick to have a tendency to rotate about point A. So in order to go from here to here for this particular system, I'm going to draw an intermediate concept. So let's say this is the same stick with the person holding on to it, and that's point A. So I have this same force here. I have to draw that. Now, if I were to add an equal and opposite force at point A, meaning this F and this F are the same in magnitude but opposite in direction, and I'm going to add another F right here. So this particular system, let's call that system number 2, is equivalent to system number 1 because these two forces will cancel out, and in essence just leaves me with this force, which would then make it the same as system 1. So the next step is to visualize this in this fashion. So let's say we have the same stick with the person holding it at point A, and I know that this force and this force is a couple, and it creates a couple moment defined by the formula that the couple moment is equal to D times the magnitude of F. If we apply the right-hand rule, where I direct my fingers along D and sweep it in the direction of F, my moment would go into the page. Therefore, I would have a negative F times D. So this is the couple moment. So I'm going to draw this force exactly where it was in the previous system 2. And this moment is a couple moment, and we know that couple moments are free vectors. Therefore, I can place it anywhere along here, and I can choose it to be right there. So this is my couple moment. So what we've done is now reduce this single force system into an equivalent system shown in number 3 here, consisting of a single force and a single couple moment. And that meets our objective right here. We now know how a single force acting on a body can be simplified to a single force and a single couple moment shown in system number 3.
So what we have here is a system consisting of multiple forces, a couple of 200 newtons, and an applied couple moment of 100 newton meters. And the objective here is to be able to simplify this system into a single force and a single couple moment. What I'm going to show you is a proof that this is possible. Then what I'll show you is a shortcut method on how to go about doing this, creating a single force and a single couple moment such that it's equivalent to this system. So what you have to do is you have to take each force and create a couple at the point of interest. So let's say we're interested in point O. So for force 1y, I have to create a couple. So I have to create a force that goes upwards. So that'll be F1y. And I also have to create this component right here. And we'll call that F1y, which is 750 newtons. So we calculate the couple moment due to force F1y to be 1.25 times 750 newtons. And that would give us 937.5 Newton meter. And to determine whether it's positive or negative, use the right hand rule. Direct your fingers along the moment arm, swing it in the direction of the force, and you see that the moment vector goes into the page, therefore it's a negative value. Next we take this F2y and do the same thing. So since that's going upwards, to create a couple, I have to make it go downwards. So we'll call this F2y, but I also have to create an equal and opposite force. So we'll call this F2y, and that has a magnitude of 400 newtons. And I calculate the couple moment due to F2y, and that would be the moment arm of 1.5 meters times 400 newtons. To determine whether that's a positive or negative, I take the moment arm, swing it in the direction of F2y, couple moment vector comes out at you, so that would be a positive. So that would be a positive 600 Newton meters. You know what, I'm going to change this. This actually needs to be 2.5 meters. So this would make it 2.5 here, and then that would measure out to be, or that would calculate to be 1,000 Newton meters. Okay, next force is F2x. I create a couple at O, so I would have to have a force going that way. That would be F2x, and I have to create an equal and opposite force like that. F2x, which is 300 newtons. We have to calculate the couple moment due to F2x. That would be these two forces right here and right here. I can draw a line of action of F2x, and we know that's 1 meter. That would be the moment arm. So that would be 1.0 times 300, and that would be Newton meter. To find out whether that's a positive or negative value, I take the moment arm 1, meters. Direct my fingers on it, sweep it in the direction of that 300 Newton force. Couple moment goes into the page, so therefore that would be a negative. So that would be a negative 300 Newton meters. This couple, F3, I can just determine by taking this moment arm and multiplying it by the force 200 Newton, and that would be a positive couple moment. So that would be a positive 1 times 200. That would give me 200 Newton meters. And finally, we have the applied couple moment of 100 Newton meter here, and that's in the negative direction. Therefore, that would be a negative 100 Newton meter. Negative 100 Newton meters. So we have to add them up. We get the sum. The sum of all the couple moment would give us actually the resultant couple moment. And if you add that up, it comes out to be 137.5 Newton meters. The next step now is to take care of these remaining forces. So let's calculate the resultant forces at O. So at point O, we have the resultant force in the x direction, and that would only be that 300 Newton force. The resultant force in the y direction would be these two forces, so that would be a positive 400 newtons minus a 750 newtons. That would give me negative 350 newtons. And we can simply calculate the resultant force, which would be 300 squared plus a negative 350 squared. That would come out to be 461 newtons. And furthermore, we should be able to calculate the angle that it makes with the positive x-axis. So here's my x, my y. I can draw my x component, which would be right there. My y component in the negative direction, minus 350 newtons. And my resultant would be this. And to calculate that angle, theta is defined by the inverse tangent of opposite, which would be 350, over adjacent. And theta will calculate out to be, so theta should calculate out to be 49.4 degrees. So what that means is that this particular system where we had a lot of forces, a couple, and an applied couple moment can be reduced to a single force and a single couple moment as follows. So we have our system, new system here, and we have our resultant force of 461 newtons at 49.4 degrees. And an applied couple moment of 137.5 Newton meters. So we would have a resultant force at an angle of 49.4 degrees and an applied couple moment of 137.5. That would be in the k direction using an x, y coordinate system. That previous method was a little too long to do, and I just showed it as a proof that you can do that. So this is a shortcut. What you want to do is, given any system consisting of forces, couples, and couple moments that are applied, if you want to replace it with a single force and a couple moment, you do the following steps. Okay, step 1. You look at your force system and you calculate the resultant force. Okay, so find the magnitude of the resultant force. Okay, so given our coordinate system xy, we're going to find the sum of all the forces in the x direction that will give us this resultant force in the x, and that's just simply this component right here, this component right here, minus 200 plus 200, and that's it. So our resultant force in the x is 300 newtons. We do the same for the forces in the y direction. So we want to find the resultant force in the y. That would mean I would have to take this force, add this force. That would give me negative 350 newtons. So I now have my x component of my resultant force, y component of my resultant force. I can find the magnitude of my resultant force, and that would come out to 461 newtons. So that's step one. Step two, what you now need to do is find the angle. Find angle of FR. Okay, so need to find the angle of that resultant force. That would give us the following. So we have this x component in the positive direction. That will be 300 newtons. And this y component in the negative direction. That would be minus 350 newtons. And of course, this would represent the resultant force. And what we want to do is find this angle right here. So theta is the inverse tangent of opposite, which is 350 over adjacent. And that would give us an angle of 49.4 degrees. Okay, step three. We've taken care of all the forces. Now what we need to do is compute the resultant moment at the point of interest, which would be point O for this problem. So we want to find the resultant moment at point O, and that would mean I need to take the sum of all the moment about point O for each force. And don't forget, if there's an applied couple moment, we have to add that too. So take the sum of all applied couple moments. So if we do that, what we have is as follows. All right. So we want to find resultant moment at O. That would mean it's this moment arm times 125. So 1.25 times 750, that would be a negative. Next, this 400, that would be a 2.5 times a 400, it'd be a positive. And then for this one, it would be a 1 meter times the 300, and that would be a negative. And then this applied moment right here, that would be 100, and that would be a negative. And the couple moment due to this couple would be 1 times 200, and that would be a positive 200 Newton meter. You add all that up, it should come out to 137.5 Newton meter. So as you can see, we actually have the same force in the same resultant moment as we had done in the proof. So what we can do is replace this entire set of forces and couple moments and couples into a single force that looks something like this. That would be our FR, and it's at an angle of theta, where theta is 49.4 degrees, and we have this applied couple moment, 137.5 Newton meters, and that was calculated to be positive, so it's going to go in the counterclockwise direction. So there you have it.